Hello, everyone. Welcome to another discussion on our series on neuroscience and neural networks. We have jumped into the neural networks part of the module, and we started off with a simple modeling of the neuron. We defined certain equations that govern the functionality of this neuron. We said there could be inputs, single, multiple inputs. Those inputs would get added at the neuron, and then that sum would then be compared to a threshold, and if it satisfies the threshold, we'll have a positive outcome. Otherwise, the neuron would not fire. We tried to relate that with the neuroscience neuron that we studied off earlier on. And then we moved on to defining certain decision boundaries for these neurons. What are these decision boundaries that these neurons govern? In our discussion, we kept our scope limited to linearly separable inputs. Okay, so now when we progress our discussion, and as you're aware, this is a recap of our live lecture session. So just to summarize our discussion here, we began with understanding that yes, there could be multiple combinations of neurons. We introduced the concept of hidden layers, that there is a sense of a hidden layer between the inputs and output, and the way they could behave could be different. And there could be multiple hidden layers. We said that there's an element of bias in every neuron, and these biases are there for each neuron. Okay, and we incorporated those in our equations. We then took an example of a neural network that had multiple hidden layers, and we said yes, there are multiple combinations that are possible. The goal, however, was to identify that if you have inputs such as these, okay, you have some data points set up like this, and this is one dimensional, you could obviously identify a decision boundary that distributes these points on either side. Okay, but if you had an input data such as the one right here, then it would become difficult to set up one decision boundary to separate them. We looked into one case where we could introduce another dimension in this data. Okay, so that would require you to manipulate the data, introduce a y-axis to each data point. We said maybe multiply these data points with a curve like this, so that each data point moves up like this in a smiley face, and then you could introduce one decision boundary separating the 2 points or the two classes. Okay, but we didn't exactly do this. We discussed and debated on this, but the more convenient idea of separating the two classes of, or coming up with decision boundaries, was to come up with two decision boundaries that would separate these classes. We looked into a particular example, which was the XOR gate implementation. So you have these inputs and you have corresponding outputs. If you see that graphically, this would mean that you would want to separate these red data points from these black data points. And we said that yes, we could draw these two decision boundaries, something like around here, so in order to separate them. Okay, in our discussion, we said we first gave it a try with the single neuron to find out one decision boundary, but we ultimately came to the conclusion that one decision boundary would not separate them. Then we listed out these three equations that you could use either of these to form these decision boundaries. The difference between them was from our earlier session. This includes the weights, this is without the weights, and the third one has the bias as well. Of course, there are thresholds that these get compared to. There was a practical example in Haken's book as well on this with the exact numbers. You're all encouraged to follow this. This is in fact the decision boundary that has been set up to separate these 2 points from these 2 points. Okay, so we were able to implement them. We verified with our calculations that yes, indeed, this particular kind of neural network with these biases and the weights set up as ones are in -2 and 1 here are in fact resulting in these decision boundaries separating out the classes that we intended to. Okay, you're all encouraged to solve this on your own as well. Then we moved our discussion to different kinds of activation functions that could possibly exist. Okay, so up until now we've been only talking about hard limit, which was to have the neuron output as a 1 or a 0, but we said that there are different activation functions that are possible, which could result the output in a +1 and a -1 as well, instead of just 0 and 1. Okay, and then there are other possibilities as well. So there is a set of activation functions and their corresponding names in MATLAB as well that are available in table 2.1 of Hagen's book. Then we steered our conversation to the perceptron learning problem, where we said that suppose you have some data points available to you and you want to identify what weights would you need to bring up a decision boundary that would separate this filled hole point from these unfilled holes. Okay, and here we took an example of inputs that are not binary in nature. You have +-1, you have 2 here as well, and then you have these targets. So the targets, such as 1 for this and zeros for this, would mean that the output of the neuron, you would expect them to be 1s and zeros. So that tells us that the activation function that we are looking at is in fact the hard limit activation function, okay, because the outputs are zeros and ones. With that being said, we first came up with a decision boundary, but we also observed that to come up with a decision boundary and to test that decision boundary would require that we assume or take some random weights. Okay, so we took some random weights, we set these random weights up, and we passed these random weights in our neuron with the inputs. We took these inputs one by one and we figured out what is the output. So we just followed this equation right here for a simple perceptron, and we figured out whether or not these inputs result in the target output with these randomly taken weights. And we looked up the first point, 1 comma 2. So 1 comma 2 with these weights, 1 minus 0.8, multiplied them, summed them up, compared them against a threshold, did not satisfy, so the output would result in 0, whereas the target was 1, so it did not meet the requirement, which meant that we needed to readjust our weights. So we need to make a change in these weights, and that would actually mean that we would have to move our decision boundary. Okay, but how do you move this decision boundary? What rule should you follow to move this decision boundary? So we developed an intuition that perhaps these weights are in fact a vector that is perpendicular to our decision boundary. Or you could think of it the other way as well, that the decision boundary is perpendicular to the weight vector. Okay, so this is not the exact length, but it's just a direction of the vector. So 1 comma 0.8 is something like this, and this vector is in fact yielding a decision boundary that's perpendicular to it. We verified this as well by plugging in the inputs x and y of these points using the same weight to see whether or not they actually fall on either side of the decision boundary, and yes, they did. Okay, so the third point did fall below the decision boundary, resulting in 1, whereas the other two resulted in zeros because they were on the other end of the decision boundary. However, this is not what we wanted because this is not our target. So to get to our target, we wanted to move the decision boundary slightly on the left hand side. We came up with a rule for this. So we said if our target was 1, which is in this case, our target is 1, but if the output is 0 corresponding to it, if that's the current scenario, we would just add our input to the old weights. Okay, so that was the input 1 comma 2, right? So that's the input 1 comma 2, and we're just going to go ahead and add this input to our originally randomly chosen weights, okay, resulting in new weights. So we got these new weights. Again, we tested these new weights, and we figured out that for these new weights, this is the outputs that we get. Okay, so the first point satisfies, but the last 2 points do not satisfy. Okay, again, we needed to update our weights so that the second point also satisfies. We looked into the rule again. The rule says that if the target is 0 and your output is 1, so your output is 1, but see that your target for the second point is 0. Okay, so in that case, you need to subtract the input. So which is what we did. We subtracted the input from our newly updated weights. Okay, These were our updated weights, and we subtracted the input of the second point this time, because it is the second point that is not meeting the target. That being done, we got a new updated set of weights, and then we use these to verify if we get the right target output. We managed to get it for the second point, but the third point did not meet it. So we followed the same process for the third point, and we needed, and there was a confusion. Should we add the weights this time, or should we add the input, or should we subtract the input? Having done both things, so we just looked into the rule this time around, and the rule was that the output was 1, whereas the target was 0. So if we scroll back up and see the target again, so the target is 0 for the third point, but the output that we are getting for the third point is 1. Okay, so output 1, target 0. We should subtract the weights instead of adding them. So we subtracted the weights, the input again from the new weights, and we got the updated weights. Using these updated weights, we ran through the network again, and we followed that yes, indeed, we do meet our targets. And that was eventually the decision line that we had, and this actually satisfied our problem set as well. Okay, so we said that, and with this example concluded, this is also available in on page 88 of Hagen 2014 book as well. The same example, you're encouraged to go through that as well. So we said that for a two-dimensional set, the input, it's okay to visualize the decision boundary like this, but when it comes to 3 or higher dimensions, it's hard to visualize the decision boundary. But regardless of that, you have the option to always plug in your weights and get your new set of outputs and compare them with the target to see where your decision boundary is and what rule you need to apply to update your weights. All right, with that, thank you.